the problem 2, we are given 3 functions, and to check whether they can represent an autocorrelation function of a wide sense stationary stochastic process or a spectral density. And if based on the property, we know that if R tau is the autocorrelation function of a wide stationary stochastic process xt, then we know that R tau is even function, and R tau is smaller than R tau at 0, and its Fourier transform of it, which is the spectral sum, is non-negative. So we need to check whether the function satisfy those above condition, which is even, smaller than value, the peak value at R0, and non-negative, to check those 3 conditions. For the first function, we can easily plot it. It is like this shape, and this is 1. And we can see that it is even function, and its peak value is it's 0, and it is also non-negative. So for the function A, it can represent an autocorrelation function and the spectral density. And for the function B, fv is equals to sine power of 2 of v divided by v the power of 2. And we can easily verify that this is an even function, because both the numerator and the denominator is the power of 2. They are all even, so the division of them is even. And since the function has no definition at 0, to calculate its value at 0, we need to take the limit, and it is equals to 1 greater than fv at v is not equals to 0. So we check it is even, so it can represent autocorrelation function. And the Fourier transform of it is also even. Which I calculate from the online calculator. So it can also represent a spectral density. And for the third function, which is equals to 1, like the impulse function when v is the absolute value of v is smaller than alpha, and 0 when the absolute value of v is greater than alpha. And we can say that the Fourier transform of fv which is also calculated by online calculation, is equals to 2 sine omega alpha divided omega, which is not non-negative because omega is equals to, like, alpha omega is equals to minus is equal to 1.5 pi, and fv is negative, so it cannot represent autocorrelation function. And since the Fourier transform and since the fv is greater than 0, so and fv is greater than 0 based on its definition, so it can represent the spectral sum, spectral density, I'm sorry. And this is for the problem 2, which is we need to know the property of R tau to be a valid autocorrelation function of a y stationary process xt. And also we need to know the Fourier transform of R tau is the spectral sum.